At the completion of this course, you will be able to identify how typical sensors and switches detect and communicate operating conditions, identify the construction and operation of sensor circuits, identify engine outputs, actuators, motors, relays, and indicators, and identify how to troubleshoot sensor circuits. Many vehicle systems, such as electronic stability control, fuel injection, and the transmission, use computers, often referred to as an electronic control unit, ECU, ECM, or PCM. ECU-controlled circuits have three requirements in order to operate. Inputs, any device that provides information to the computer. Logic, based on the input information, the computer makes pre-programmed decisions on how to control an output device. And outputs, a load controlled by the computer. The ECU will usually turn an output device off, on, or control the amount of on and off time. Let's look at the engine management system. Sensors provide input signals to the ECM for engine operating conditions, such as engine load and coolant temperature. Using built-in logic, the ECM controls outputs like fuel injectors and ignition coils. It's useful to think of the ECM as a high-tech voltmeter with a built-in stopwatch and a switch. Why? Because the ECM reads input signals in the form of voltage, measures how long each signal is present and at what frequency, processes the information based on its internal programming, and responds by turning actuators on or off to an internal set of instructions. In this course, in addition to demonstrating how computer-controlled circuits operate, we will also show you how the circuit data appears on the scan tool. As we discuss each type of sensor and output, note that the data from the ECU and the way it is displayed on the scan tool is not always the same format as the signal from the sensor. For example, the engine coolant temperature sensor outputs a variable voltage signal which is displayed on the scan tool screen as degrees Celsius or Fahrenheit. It's clear that a conversion process is taking place in the scan tool. The ECM processes a number of common types of signals generated by the input sensors. Let's look at the 5 most common types of input signals and the sensors that generate them. On-off state sensors are actually switches or relays that report their position as either on or off to the ECM. Their state can be changed in response to changes in position, temperature, or pressure. Components that use on-off state sensors include brake switch, AC pressure switch, AC triple switch, ignition switch, clutch switch, cruise control switch, and range control switch. Depending on the system, the switch may apply either power or ground to the ECM. The AC triple switch is an example of an on-off state sensor. This sensor responds to changes in refrigerant pressure and is used by the control module to protect and control the AC compressor. With variable voltage signals, the output voltage varies continuously in response to changing conditions. For example, a throttle position sensor changes the output voltage as you depress the accelerator pedal. Variable voltage signals are sometimes referred to as analog signals and include thermistors, variable resistors, and voltage generator types. Sensors that use variable voltage signals include oxygen sensors, engine coolant temperature sensor, inlet air temperature sensor, throttle position sensor, manifold absolute pressure sensor, mass airflow sensor, accelerator pedal sensor, fuel tank pressure sensor, knock sensor, power steering pressure transducer, AC pressure transducer, oil temp sensor, and the fuel level sensor. The engine coolant temperature ECT sensor's output resistance is monitored by the ECM-PCM to regulate ignition, fuel, and emission control functions. The sensor is a negative temperature coefficient, or NTC resistor, in which the resistance goes down when temperature increases. Variable voltage can be supplied to the ECM by a sensor with a variable resistor, known as a potentiometer. The throttle position sensor is a variable resistor that indicates the electronic throttle control motor position, which relates to the opening of the throttle valve. In an electronic throttle control system, two TPS sensors provide the ECM with two separate voltage signals to detect the change in throttle valve position. By having two sensors, the ECM can also compare both voltages and detect problems. A heated O2 sensor, or HO2S, is another type of variable voltage signal sensor. This sensor generates a voltage signal based on the amount of oxygen in the exhaust gas. Variable reluctance AC signals are used to measure position and speed of components. These sensors generate a signal that is proportional to the rotational speed and position of the metallic component being monitored. The signals generated are an alternating current as opposed to direct current. Sensors that use variable reluctance AC signals include the crankshaft position sensor and some wheel speed sensors. The crankshaft position sensor can be a type of variable reluctance AC sensor. It is an inductive type sensor mounted in the bell housing. It generates an AC signal using a target wheel mounted on the flywheel. Using the signal differences caused by a longer slot, the ECM can identify when the cylinder is at top dead center. Hall effect sensors use transistors that are sensitive to changes in magnetic field and generate a square wave output signal. They are used to measure the speed and position of rotating wheels and shafts. These sensors require an external voltage source with a typical signal voltage of 0 or 5 volts. Hall effect type sensors include crankshaft position sensor, camshaft position sensor, wheel speed sensor, vehicle speed sensor. The crankshaft position sensor, or CKPS, a Hall effect type, generates a voltage using a Hall sensor and a target wheel mounted on the crankshaft. There are 58 slots in the target wheel, with one slot longer than the others. When a slot in the wheel aligns with the sensor outputs a low voltage. When a metal tooth in the target wheel aligns with the sensor detects the magnetic field and outputs a high voltage. You can see this signal gap when viewing the waveform on an oscilloscope. During one crankshaft rotation, there are 58 regular signals and one longer signal. The PCM calculates engine RPM by using the sensor's signal and controls the injection duration and the ignition timing. Using the signal differences caused by the longer slot, the PCM identifies which cylinder is at top dead center. Frequency signals indicate changes in voltage per second. The output signal from this type of sensor is measured in hertz, the letters Hz, or cycles per second, the letters CPS. Sensors that use frequency signals include the mass airflow filter and the alternator. Current vehicles that use a MAF sensor direct incoming air across a heated wire. The resistance of the wire decreases as heat from the wire decreases by the air traveling across it. The MAF sensor measures the voltage drop across the wire, and an internal amplifier outputs a varying frequency that the ECM uses to calculate the mass of the air entering the throttle body.